All right. In last week, we talked about the concept about threshold voltage. What is that? For example, this is some kind of MOS. From the very beginning, we have two parasitic diodes connected back to back. It means the bias interaction is reversed to each other. So from the very beginning, it is not conductive between source and drain. But how to make such kind of enhancement type MOSFET conductive? Actually, you need to kill those two parasitic diodes. But how? For MOS, you need to apply positive voltage, right? To do what? To attract negative free electrons here. Yeah. First of all, to recombine all the free holes here because it is P substrate. It is P type. We need to make it intrinsic. It means neither P type nor N type. Okay? So the voltage you need to make the region from P type to intrinsic, it is the threshold voltage. Okay. And after that, you can attract more free electrons. Anyhow. Okay. If the voltage here is larger than VTH, then the higher above VTH, the more free electrons you can attract to line up beneath the gate oxide. Okay. To make the region again from intrinsic to N type, and you have N type, N type, and N type. So right now, it is conductive between source and drain. Okay? Then, how about the threshold voltage? Actually, this is the equation for threshold voltage. Anyway, it has two terms from solid-state circuit. I would like to express my concern about this term. How much voltage you need to apply? Okay, let's go back from the very beginning. What is the definition for threshold voltage? The voltage you need to apply to attract the exact number of free electrons to kill the free holes in that region. Okay, and I told you already, MOSFET, actually, it is some kind of capacitive device. Without capacitance, it doesn't work. It depends on capacitance very much. And where is the capacitor? Oh, the main capacitor is here. Above it, we have a gate. It is conductive. Below it, we have the so-called channel. It is also possible to conduct. Okay? In between, we have the so-called insulator. This one, silicon dioxide. So, why not? That is something, we call it parallel plate capacitor, 平板电容. Okay, so according to the definition of ideal capacitor, we have Q equals CV. Okay, the number of charges equals capacitance by voltage. Okay, so what the definition again for threshold voltage? The exact number of carriers you need to attract, okay, to kill all the free holes here. So you can see how many free holes. It depends on doping concentration, right? It means what? The higher doping means the more carriers you need to attract. So it means what? The higher voltage you need to apply. So the threshold voltage, you can guess, the threshold voltage proportional to what? The doping concentration. Okay? And then, again, so we have this one. Q, depression region. The number of charges in depression region, so it is proportional to the doping concentration. And also that, if we go back to here, right now, depression region, right? Okay, VTH, that is the definition. So right now, we know exactly how much doping it is. Then, how much voltage you need to apply? Oh, very simple. Divided by C. Right, that's it. Okay? Bingo. So, I try my very best to explain why VTH has this term. It is very important. For all of you, I think you would like your MOSFET to run faster. Okay? But how? You need to reduce VTH. How to reduce VTH? Two ways. First of all, to reduce the number of hours in depression region, blah, blah, blah. Okay, anyway, to reduce the doping concentration. The lighter doping, the better for conduction. 越轻掺杂，越容易导电. And this is the reason why we have P minus for substrate and M minus for N well. Okay? That is the very fundamental requirement for such kind of CMOS process. Then, if you try your very best to reduce the doping concentration, and then what you can do? Oh, we can increase the capacitance for gate oxide. So we call it C oxide. Okay, C ox. But how? Okay. Again, let's go back. How to reduce it? According to the definition for capacitor, okay, we have capacitance, right? And what is C ox? Capacitance per area. Per area means you need to divide by A, right? Oh, congratulations. So C ox equals epsilon dielectric constant, 介电系数, divided by D. The distance between what? The top plate and bottom plate. So it means what? The thickness of silicon dioxide. 这是上下两板中间的间距，这是二氧化锡的厚度。Okay, the thickness of the silicon dioxide. So how to reduce it? Again, two ways. Either you, sorry. How to increase it? Sorry. We need to increase it. Okay? So how? First of all, to increase the dielectric constant, 你必须提升介电系数. But how? By doping. Okay? Doping can also change the constant very, very much. From the very beginning, silicon itself for epsilon, I guess, is around 13 or 14. But by if you make it become silicon dioxide by oxidation, 把它氧化之后多了氧原子, then it is reduced to about 4. Okay, 3.9 or 3.8. Anyway, silicon itself 13, but with oxygen it's reduced substantially to 4. Is it good for you? No. If you are talking about the dielectric constant for silicon dioxide, we hope we can increase it. But how? Again, try to dope some other impurities. That's it. So that is the so-called high K material. Okay, high K. We have high K, so it means what? We have low K. Low K for what? High K to enhance the C oxide here. Okay? But we still need low K. Why? Between metals. Metal 1, metal 2. Okay? Metal 1 and metal 2. Metal 1 and metal 2. They are also conductive. In between, we have silicon dioxide as insulator. So you have another kind of parasitic capacitance, right? We would like to reduce it because the parasitic capacitance between metal 1, metal 2, metal 3, they will kill the performance of your delay. They will enlarge the delay. So we will try to reduce it, but we would like to enhance the capacitance here. So it means we need to have high K insulator here and low K insulator for between wires. That's it. Okay? Yeah. So you can see that analog IC design, analog IC layout, they are strongly correlated. IC 类比 IC 设计跟布局事实上它们有非常强的那个相依性。You need to know both, otherwise you cannot design outstanding all the so-called high-end analog chips. Okay, so this is what I can help. All right. I try to explain without any derivation. That is the best you can learn from myself. Yeah. For derivation, you need a lot of background knowledge from solid-state circuit, blah, blah, blah. That is too hard for most of the students. So I am more than glad to explain everything instead of derive all those issues for you to save your time. But with explanation, with good enough explanation, I think you can learn more, okay, than derivation. Usually, after derivation, blah, 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 you have tens of equations, you get the final equation, but you forget the meaning, the function of the equation. All the equations are used to convince yourself what we talk is correct. That's it. Okay? And don't ask me, for all those analog chip design, you derive first, then design. No. We always design without any derivation, unless you have very specific structure, just like PLL. It has complete theory for circuit design. So you need to derive the equation first, or analyze. Yeah, because all the equations were derived tens of years ago. But how about the parameters? Yeah, especially for loop filter, you need to know, okay, which order, second order, third order, blah, blah, blah. Okay, anyway, that is very unusual. You need to at least analyze the equation first, then design. That is really, really unusual. Okay, for most of the analog circuit, usually we don't derive, we don't analyze anything. We simply go design. Okay. Right. And then I can go further with explanation. As I mentioned already, if the gate voltage is higher than threshold voltage, right, then it means what? We can attract extra free electrons to line up in this region to make the so-called channel. Then source and drain are connected. Congratulations. And you need to know who dominates the conductivity. Channel. Why? Because source and drain, they are heavily doped. So it means what? Their conductivity is much higher than this one. Got it? Okay? So channel dominates the conductivity. So from the very beginning, you can see what shape the channel is. It looks like this. rectangular parallel piped. Okay, parallel pipette. Yeah, 长方体. Okay, so you can see. Allow me to show you this. Again, you need to know what is the mapping between the device and its layout. From the very beginning, you have again this the gate, okay, and then the source and drain, okay, and where is the channel? Ideally, the overlapped area, okay, beneath the gate oxide. Here, I mean here, okay. I mean ideally, just forget about the side etching. Otherwise, yeah, it will be shortened. The real area will become here. Okay, this and that for side etching. Forget about it. Okay. Then what is the shape? Actually, we have the so-called width. Here is the width. Okay, and ideally the length. Yeah. Here, this is the length. Okay. Yeah. From here to there, that is the length because the majority carriers needs to go from the distance. Yeah, you need to go from source to drain. So ideally, from here to there, that is the length. Okay, so allow me to take out the channel for you. Just something like autonomy. Okay, 我帮你解剖，然后把 channel 拿出来。Here is the shape of the channel. Okay. Width here, length there, and how about height? The height actually depends on this, right? The depth of the channel. I told you already, the more you above threshold voltage, the more carriers you can attract here, right? It means what? You have thicker. The higher above threshold voltage, the thicker the channel will be. That's it. Okay, so you can see the channel depth, okay, is proportional to this one. Please keep this in mind. It's very important. So overall, how about the resistance? You can see, this is, because again, I told you, the channel itself dominates the conductivity or dominates the resistivity. Okay, so what is the resistance of the channel? What is the conductivity? According to resistor, yeah, I mentioned it last week already, it looks like this. Sorry. Right? This is the length. And what is the area? This is the area, the cross-sectional area. 纵剖面的面积. So what is that? W by width. By depth. Sorry. Yeah, width by depth. Okay. So you can see the resistance is reversely proportional to the depth. And the depth is proportional to VGS by VTH. Got it? Okay. All the conductivity. If we are talking about the conductivity, always we have G. Okay? It will be proportional to this. Bingo. That's it. Okay. So, you can see ID over VDS. Okay? From the very beginning, we have such kind of shape, three-dimensional shape for your channel. Okay, and the conductivity of such kind of channel, I told you already, is proportional to this. The higher VGS over VT, the better conduction. We call it overdrive voltage. Okay? Overdrive. 过驱动. Or sometimes we call it excess voltage. 超过的. Okay, anyway. So, allow me to explain this for you. If your VGS equals VT, sorry for that. 0 depth here, no conductivity, right? In theory, okay? And then you increase it 1 volt higher, 2 volt higher, 3 volt higher, wow. The conductivity is proportionally increased. 过荷电压 VG 超过 VTH 越多，你的导电度越好。And what is the conductivity? Oh, the slope. Because that is I over V, right? So the slope will be proportional to this. Got it? For our IV curve from the very beginning, the slope of your IV curve will be proportional to VGS minus VTH. So that is the first concept I would like to explain to you. However, this is not any kind of fairy tale. 他们不是童话. So you're going to say, hey, they live happily since they have... No. Only for the very beginning. When VDS, when the voltage between here and there is really small, then we don't have any kind of deformation, 变形. For the channel still, if VDS is really small, I mean close to 0, we don't have any kind of deformation for such kind of rectangular parallel pipette. Okay? So we can still enjoy such kind of characteristic. I mean the slope of the IV curve is proportional to this from the very beginning. However, if you increase the drain voltage higher and higher, then sorry for that, we don't have such kind of rectangular parallel pipette. Instead, we will have some kind of deformation. Okay. Okay. Let's go further. Where? Wait, sorry. Oh, okay. Here. From the very beginning, if VDS is really small, then we have such kind of rectangular parallel pipette. However, if you increase the voltage here, then what? You can see for the VG, it is constant. Okay, assume it is constant. Okay, and how about the voltage from source to drain? Because right now, usually we have source as the reference point. Okay, for explanation. Yeah. So usually that is concept for the so-called common source. Okay, common source means a source as as the reference point, and where is the input? Usually gate, because gate is used to control the conductivity, right? So what is the output? Usually drain. Okay, so that is from the very beginning, common source is commonly used. 从最开始我们就把 source 当作参考点，所以那个是 common source 的一个架构。Anyway, allow me to explain here. The gate voltage here and source as the reference ground. Okay, if you apply too much voltage to drain, the voltage between source and drain will look like that. Okay, this is the drain and that is the gate. What I told you, for each point of the channel, here, over there, I don't care. For each point, how much depth it has, it depends on the voltage difference between the gate and the gate voltage here, right? Okay, so for each point, here, 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 over there. What is the channel depth? It depends on the voltage difference between the gate and the potential of this point. Okay? And again, as I mentioned already, if in I told you already, the channel depth by VTH, right? But right now, we are not talking about source because we are not always here. No, we try to move from source to drain. So if for each point, for any of the point, you label it as X, then you can change it VGX minus VTH. Oh, bingo. Okay. So if you go from the source to the drain, you will see the gate voltage here, but the voltage along the channel will be increased. So it means what? This one will be reduced linearly. Okay? So it means what? The channel width, the channel depth will be also reduced linearly. Okay, so from the very beginning, as I mentioned already, you have this type. Rectangular parallel pipe. Okay? We assume VDS very close to 0. You have such kind of shape. However, if you increase the voltage at drain, sorry for that, it will become this one. The channel depth will be reduced from source all the way to drain linearly. Okay? So finally, you don't have the rectangular parallel pipette. Instead, you have such kind of trapezoidal parallel pipette. 梯形体. Okay? So it means what? The higher the drain voltage is, the cross-sectional view will become from here to there, to there, to there, to there, to there. The higher voltage for drain, yeah, it will look more than that. So the bottom plate will be changed. Okay, all the way. So what is the impact for your conductivity? Again, conductivity, yeah, or resistivity as you like. Okay, for resistor, is proportional to length and this one. Okay, so for conductivity, it is proportional to area by length. Anyway, you can see from this one to this one, or even to, okay, the length is still the same. We have the same length. The top plate, the bottom plate is increased from here to there. The length is still the same. But the average channel depth will be reduced. Got it? So how about the conductivity? Since the length is the same, but the channel length or the average channel length, channel depth will be reduced. That's it. So the higher drain voltage, the less cross-sectional area. So the less conductivity. That's it, what I can help. Okay? Don't expect the linear dependence between ID to VDS will be exactly linear. No. From the very beginning, it is linear. But after you increase the VDS, as I told you already, the conductivity, proportional to area by length. It is fixed, but it will be reduced. The higher drain voltage, the less cross-sectional view, it means the less conductivity. Okay, so if you go from 0 volt to higher volt, the higher voltage means what? The less conductivity. Okay, So what is the tendency for this? If without deformation, it will be linear. Okay, but the higher voltage, the less conductivity. Got it? Definitely, it will look like this instead of that. All right? If no deformation, you will have this one. With deformation, 变形，越来导电率越差。So it means what? Less current than this one. Okay? So it will go in that direction instead of this direction. No. Okay? So I explained this already for you. Here we zoom in, look like that. Okay? But without zooming in, you can see the slope will be decreased all the way. And finally, here, it will be saturated. Why? Because the cross-sectional here will be reduced from here to there, to there, to there. And finally, the depth at drain is 0. When the depth will become 0 at drain, the voltage between gate and drain is exactly one threshold voltage, 1 VTH. That's it. Okay? So it means how to make it from rectangular to become triangular. 怎么把这个由长方形变成三角形? The point here means the VT needs to be VG minus VT. Got it? VTH. And I told you already, usually source is the reference point. Okay? So it means VDS equals exactly VGS minus VTH. Bingo. So, what is the saturation point? Here, the voltage is exactly VGS minus VTH. Bingo. So, guess what? What is the saturation current here? From the very beginning, the slope is proportional to this. Right? Okay? Just like running. We are racing? Yeah. If I can run faster than you by 3 times, and then I can run 3 times more than you. So how is the total distance I can run compared to you? 3 by 3. From the very beginning, my slope, my speed, 3 times higher than you. You can only run 1 hour. I can run 3 hours. Wow! So 3 by 3. The square of 3, right? So, for the current, from the very beginning, it is depends on the slope, depends on this. And how far I can go? Another VGS minus VTH. So, the saturation current is proportional to the square of this one. Bingo, that's it. Okay? So, I try my very best to explain why the saturation current look like. Which one? Where is the equation? Oh, this one. Oh, finally. Yeah. Got it? And when the depth at drain becomes exactly 0, we call it pinch off, 夹指. Okay? After saturation, in theory, because the current is saturated, 电流已经饱和了. It means what? It won't be increased anymore. So we have such kind of IV curve. Again, from the very beginning, it is linear. But if you increase the VDS, then you will become, and finally, flat. So the point from here to there, yeah, the interface, we call it pinch off point. Before pinch off, we call it triode region. And after that, we call it saturation region. And again, in theory, I am talking about in theory. Okay? It is saturated. 它已经饱和了. So it means what? No more increase for ID. Again, in theory, not in practice. However, if you are curious, hey, if I increase the drain voltage even after pinch off, I try to increase the drain voltage. What will be the consequence? The pinch off point will be moved from drain back to source. Got it? That's it. But what is the impact? Oh, okay. Again, this is the cross-sectional view for the channel here. From the very beginning, then, oh, congratulations, pinch off. That is a saturation point. But if you further increase the drain, it will become that. Got it? The pinch off point will be moved from drain toward source. But what's the impact for conductivity? Again, conductivity proportional to area over length. Okay? So, right now, the length is reduced from here to there. Got it? And how about the average depth? Exactly the same. You can see for this one or for that one. For this one, the average is here in the middle. For that one, it's still in the middle. So they are exactly the same for triangular cross-sectional view. OK? 只要你是三角形，你的平均深度就是一半，这里的一半。Yeah. 50% of the depth at source. So after pinch off, I promise you, the cross-sectional area will be the same. However, the length will be reduced. So it means what? You will get a little bit more conductivity. Sorry for that. It means what? After saturation, after pinch off, it is not flat for the IV curve. It will be increased a little bit according to the effect. We call it channel length modulation. Why? The higher drain voltage, then the higher, the shorter length, the higher, the even shorter. Okay? So we can reduce the channel length by increase the drain voltage. The higher drain voltage, the shorter channel length. The lower drain voltage, the longer channel length. That's it. That is the concept for channel length modulation. 通道长度调变就说你可以改变 drain 的电压 ，drain 的电压越高，通道越短；电压越低，通道越长。所以you can change VD. If you change the voltage at D, then the channel length will be longer, shorter, longer, shorter. That is the definition for channel length modulation. Okay? Anyway, anyhow, the impact is the slope won't be zero. It has some kind of slope. That's it. So, the channel length modulation is what we hate because we hope it is flat here, and it means the output resistance between RDS. Okay? Output point is usually the drain. So, what is the output resistance? RDS. A source, again, is the reference point. So, RD. Okay? That's it. What is the definition for RO? Again, the differential the output current by VDS or VO. Okay? That's it. So if you change, if it is flat, never mind the larger VDS or the smaller VDS, no current difference. It should be 0. Sorry. This is GO. Sorry for that. That is not RO. For RO, you need to have DVO, DIO. Okay, you change VO, but IO, the difference of IO equals 0. So you have infinite RO. Bingo. That is what we want. Okay. On the contrary, how about GO? Yeah, DI over DO. Okay. So you change VDS. No change in output current. So you got 0 conductivity. Congratulations. That is what we need for MOSFET. But nothing is perfect. According to channel length modulation, if you change VDS, ID will be changed a little bit. So you have some kind of conductivity. And it means what? The resistivity won't be infinite. No. 不可能无限大. Yeah, it is finite. 一定有限. Okay? Yeah, that is what I can help. Till now, I explain this one. Why ID is proportional to the square of this one, of the overdrive voltage. Okay? And how about the others? Oh, you can guess. Yeah, the current proportional to the conductivity. Conductivity proportional to area by length. A length here. An area, you have width. Oh, congratulations. Blah, blah, blah. Okay. That's it. If you would like to know how to derive the equation exactly, no worries. Please go back to read your microelectronics. Yeah. It is derived there already. But again, usually for students, after derivation, they achieve this equation, then get lost. What's for? What's the meaning for this? Okay, so I try to explain why the square, okay, instead the third power, the first power, or even only the first power of overdrive voltage. No. Again, from the beginning, the slope is proportional to this. And then you can go such a long way. Okay. Before saturation, before pinch off, you can go the other one. So it is the square of this overdrive voltage. That's it. Okay? Yeah, anyway, for saturation current, you can see who will have impact on saturation current. The length, the width, the threshold voltage, blah, 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 as I mentioned here. Okay? And allow me to show you more detail about the long channel IV plot. Long channel usually means, how can I say? Hundreds of nanometers. Okay? Or even 1 micron. Yeah. Anyway, for such kind of long channel IV plot, you can see again VGS. Oh, sorry, this is incorrect. Minus VTH. Okay, sorry for that. Yeah. And you can see it is not linearly dependent for such kind of saturation current because it depends on the square of the overdrive voltage. Okay? So if you increase the VGS linearly, VGS minus VTH, sorry, okay, from 0, 1, 1.5, 2, 2.5, oh, you can see the space between the curves becomes larger and larger, okay, according to the square of overdrive voltage. That is what you can expect for long channel MOSFET or the MOSFET for old processes. 比较老的制程哈，看起来就是这种德性。Yeah, maybe for 0.18 it's still, for 0.80 micron it still look like this one. How about 28? How about FinFET? No, they are short channel MOSFET. Okay. Oh, before leaving this page, allow me to show you. Again, this is for trial. And after pinch off, we call it saturation. Oh, what's the matter? Here, for the saturation current, for the saturation region, okay? And we have cutoff. Cutoff means what? VGS minus VTH less than or equal to 0. In theory, no current at all. So here, that is the cutoff region. No current at all. However, that is only, how can I say, in theory. In practice, it conducts a little current. Why? Oh, if you go back to see the definition, right? If the VGS equals VTH, VGS equals VTH, it means what? All the carriers here are killed. Okay? So it is some kind of intrinsic semiconductor. Can intrinsic semiconductor conduct current? Yes, it is semiconductor. It is not any kind of insulator. Okay? So even VGS equals VTH, don't expect 0 IDS. No. Sorry for that. It is still a little bit conductive. Okay? Since it is semiconductor instead of insulator. 所以你这两个一样，理论上 channel depth channel 的深度等于0，它不会导电错，它只是变成本质半导体，半导体还是会导电哈，会导一点点的电。Don't be misled， 不要被误导哈。Okay, saturation, transconductance. Okay, before our short break, I would like to show you something more. At least here, you can see that after saturation in saturation region, the saturation current look like this, as I explained already. And how about the transconductance? Trans means transfer, 转移. So it means what? The output port and the input port should not be the same. You apply your signal to the input, but you get the output signal from the other point, the other port or the other node. Okay? So you can see for the gate, for the MOSFET, usually for common source. Yeah, common source is the usually or commonly used idea. Source as reference. You apply your input to the gate and you get your output from drain. Right? So input port here, output port there, they are not the same. So we have transfer. Okay? And conductance means what? Conductance means I over V. So I out, the output should be current, and the input should be voltage. That is the definition for conductance. That's it. From fundamental circuit theory, 基本电路学就教这个东西. So how to derive your GM? Oh, very easy. Yeah, because current is the output and voltage is the input to the gate, right? So we differentiate ID over VGS. Yeah, you will have this one. So if you plot GM over overdrive voltage, right? They are linearly dependent. Okay, 它们两个是成正比的. However, hey, you can see. How about this term? This term? You move this to the other side, then squared. Get the square root. Okay? Oh, you will get this one. That's it. Okay, so if you plot GM over ID, because the square root, 开根号, so it looks like that. Okay? If you would like to go further, you can see, hey, look, this term, and that term. Okay, what is this term? What is that term? You can divide ID by the squared, right? Okay, but don't forget you have the other one. So this one and that one, will be cancelled. So you get here. Got it? That means what? Wow. Again, if you plot GM versus this one, sorry. They are reversely proportional to each other. 它们成反比. Okay? So GM versus this one, it looks like that. Okay. Right now we had a big trouble. See? The first, the second, and the third, the transfer curves are totally different. Okay? Especially the first and the third. They are talking about the same thing. GM versus overdrive voltage. GM versus overdrive voltage. Gosh, they are totally different. One told you they are proportional to each other. And the other one told you they are reversely proportional to each other. Gosh, they are contradictory to each other? Is it? 你看，第一个告诉你这两个家伙成正比，最后一个告诉你他们成反比，哇，完全颠倒。Okay, so which one is correct? Which one is correct? All those are correct. However, under different situation. Okay? For the first one, ID is not fixed. It is depends on this. If you increase overdrive voltage, ID will be increased by 2 orders of the overdrive voltage. Okay? So that is for the first condition. And how about the last condition? ID is fixed. Sorry for that. Okay? Never mind how you increase it, ID is fixed. Sorry for that. Alright? So, if you increase it, but ID is fixed, what you can do? You need to reduce W over L. That's it. Okay? Unluckily enough, I guess most of the students hate this idea. Usually, for your intuition, you will think, oh, that one is correct. Allow me to point out that this one is also correct. And unluckily enough, this is the usual case for analog IC design. Because analog IC usually apply bias current. So from the very beginning, you have, how much bias current for this block, for that block, blah, blah, blah. It means what? Bias current is fixed. ID is fixed. That's it. Sorry for that. Okay? So if you would like to change overdrive voltage, you have only one possibility. You need to change the aspect ratio, W over L. To change W or to change L, that is the usual case you need to do from the morning till night, right? For analog IC design. That's it. You change this instead of the current. No. After you settle down how much bias current is, you will face this condition. Got it? So the more overdrive voltage means the less conductivity. Sorry for that. The reason why is you reduce W over L substantially. For example, if you would like to double it, then you need to reduce this by 4. Got it? Under the current ID is fixed. That is the usual case. Sorry for that. All right? So before the break, allow me to point out again, this is not the usual case for your design. That it looks so strange, but that is the usual case you need to face. Okay? Yeah. All right. We can have a short break right now.